Okay. We will discuss about the torsion of circular and non-circular sections. So in strength of materials, so you have studied about torsion of circular sections. So torsion of circular sections means suppose if a rod is subjected to torsion. So like this it is shown. So if it is in this direction at this end, it will be in the opposite direction the other end. So it is denoted by T. T is the twist or twisting moment. Twisting moment, or it is also called as torsion. So normally it is expressed in kilonewton meter or kilonewton millimeter or Newton millimeter. So 1 kilonewton meter is 10 power 6 Newton millimeter. That is the conversion. So this you have learnt in SOM. So that means at this end it is like this. Suppose if this is the rod, so at this end it is subjected to moment like this, at this end it is subject to moment in the opposite sense. Then it is subjected to torsion. So there is a difference between torsion and bending. So if you have load here perpendicular to the axis, then it causes bending. So torsion is a longitudinal moment. It is a moment acting along the axis. So this is called the axis. So normally bending moment is denoted by mz. Bending moment is denoted by mz because it will be acting in the plane perpendicular to this. Whereas torsion moment is nothing but mx because it is acting along x-axis. So that is the difference. So twisting is the effect of torsion moment, whereas bending is the effect of bending moment. So a member may be subjected to both bending moment as well as torsional moment. But here we consider only member subjected to torsion. So here when a ball is subjected to torsion like this, so suppose if I take the cross section of the member like this, so if you cut this, the cross section XX will be a circle like this. So with radius of R. So the effect of this torsion is, due to torsion, there develops shear stress here. Shear stress will be developed here. So that shear stress is denoted by tau. Tau is going to develop due to torsion. So this shear stress is expressed normally Newton per mm square or Nt. That shear stress value, it varies. Actually maximum shear stress will be at the periphery. At the periphery of the shaft here, at the circumference, you will be having the value of maximum shear stress. So tau max occurs at the periphery. This is in the case of circular section. In the case of circular section or hollow circular section. So hollow circular section means it will be like this. So these things you have learned in strength of materials. Hollow circular section will be like this. In this case also, for torsion, when it is subject to torsion, it will develop shear stress like this. So it will develop at the periphery. So maximum shear stress will occur here, and it is zero at the center. So shear stress will be zero at the center of shaft. This is in the case of circular, solid circular or hollow circular. This is solid circular section. This is hollow circular section. So due to this, what happens? The member gets twisted like this. Something like this. So an angle will be formed here. So due to this, the member gets twisted. An angle will be formed here. That angle is nothing but phi. That phi is called as the shear strain. That is an effect of torsion, shear strength, which will be in radians. And of course, in the cross section, suppose if this is the layer, this gets shifted here. This point, see here, this point B will get shifted to B dash. This is B, this goes to B dash. And there will be an angle here in the cross section. That angle is nothing but theta. So here theta is called as angle of twist. So note the difference between phi and theta. So this point has gone here. So this angle is called as theta. So that is theta is called as the angle of twist. So this angle of twist will normally be in radian. And if I take length of this bar as L is the length of bar, then we can develop one equation called pure torsion equation. Just like pure bending equation, you can have pure torsion equation. This pure torsion equation you have derived in SY. So the equation says that T by J is equal to G theta by L is equal to tau by R. So this is called as the torsion equation. Just like M by I is equal to F by Y is equal to E by R, pure bending equation, you have pure torsion equation like this. So here T is the torsion moment, which normally is expressed in Newton millimeter. J is called as the polar moment of inertia. Polar moment of inertia. For a circular section, it is given by pi d power 4 by 32, where d is the diameter. So if you convert this d into radius, then it becomes pi into 2r to the power 4 by 32. It will be pi r power 4 by 2. Because 2 power 4 is 16, so it becomes pi r power 4 by 2. This is called as polar moment of inertia. G is the modulus of rigidity of material of the shaft. Modulus of rigidity or rigidity modulus or shear modulus. It is also called as shear modulus, which is expressed in once again Newton per mm square or MPa. L is the length of the member, which is subjected to torsion. It will be expressed in millimeters. Please note that all the units are in newtons and millimeters. Then theta is the angle of twist, which is expressed in radian. Angle of twist expressed in radian. So if you know the conversion, 1 degree is equal to pi by 180 radian. Suppose if they give in degrees, we have to convert that into radians. So 1 degree is pi by 180 radian. Tau is the shear stress. Shear stress at the periphery. Of course, it is tau max at the periphery. We have the maximum shear stress. I can write as maximum shear stress. Once again, it is expressed in Newton per mm square. And R is the radius of the circular section. And we can call it as shaft. Normally it is called as shaft. So this is the torsion equation, pure torsion equation, which you have derived in tensor materials. We are not going to derive here, but if you know the rotations, T by J. So this polar moment of inertia, this will be in millimeter per second. These are the units. Yes. So this equation is called as the pure torsion equation. Using this, we have solved problems on circular shafts as well as hollow circular shafts with tensor materials. Now here we are going to have non-circular sections also. So whenever a member is subjected to torsion, please note that twist will be there, angle of twist will be there, shear stress will develop. Those two things you should keep it in mind. Now let us see how this can be applied for non-circular sections. Non-circular sections. What are non-circular sections? If the section is not circular, solid circular or hollow circular, then it is non-circular. You can have rectangle. Rectangle is non-circular. Then you have ellipse. Ellipse is non-circular. Then you can have triangular section. This is non-circular. Then you can have T section. This is non-circular. You can have I section like this. This is non-circular. In addition to this, you have tubular sections like tubes. Tubular sections means it is like this. This is a tubular section, like a tube. Some thickness will be there. This is a tubular section. You can have multi-cell tubular sections, so more than one. So these are all examples for tubular sections. So two-cell, we call it as two-cell tubular section because there are two cells, two compartments will be there. This is a single cell. You can have irregular boundary also, something like this. See, you can have sections like this also. Here also you have two cells, but it is irregular. So these are all some of the tubular sections. You can have any number of compartments, 2 or 3 compartments. What happens when these types of sections, they are subjected to torsion like this? T is the torsion. When these types of sections are subjected to torsion, how the shear stress will develop, how we can compute the angle of twist, all those things. So this is subjected to T. This is subjected to T. This is subjected to entire. The entire thing is subjected to. So what is the value of theta? Angle of twist. What is the value of the shear stress? How to find those things? That is the question. We can find out theta and tau in circular section using this formula. That is pure torsion equation. Whereas if it is non-circular, so we have to develop some equations to find the angle of twist as well as torque. So I have explained in detail in some 2-3 videos the theory behind this, and also numerical examples I have done. So anyway, today I will take up one derivation which I have not done there. So I have done elliptic derivation I have done. So normally they will ask that derive the torsion equation for elliptical cross section. So I have done that in one of the videos. Today I will take up for circular. Circular also. Of course, circular in general this is the torsion equation, but using theory of elasticity you can have a different set of equations for circular cross section also. Now let us have the torsion equation for a circular cross section. Before that, some notations we should note down. In the case of a non-circular section, what happens? There will be an additional effect called warping. So this is a new word. Warping effect will be there, which is not there in circular sections. This is important. This I have explained in one of the videos. warping means it's out of plane bending. We call it as out of plane bending. In the case of circular sections, you don't have any warping. So circular section you don't have any warping, whereas in the case of non-circular sections, so no, there is no warping here. Only twisting will be there. So twisting is in plane displacement, whereas warping is out of plane displacement. That is the difference. For twisting, in the plane, whereas warping out of plane. So in the case of non-circular sections, you have warping also. There is one function denoted by psi. Psi is Greek symbol. This is used for representing warping. This is called as warping function, which exists only in the case of non-circular sections. So this psi is equal to 0 in the case of circular sections. For circular sections, so there is no warping, therefore phi is equal to 0, whereas psi is a function of x and y for non-circular sections. And you have one more called capital phi. So this capital phi. So don't confuse with this phi with that one. Here phi is shear strain. Here phi is stress function. So this we have used. Already we have used this in both the Cartesian and polar coordinates. This is called as stress function. Phi is called as stress function. Psi is called as warping function. So both will be there in the case of non-circular sections, whereas in the case of circular sections, only phi will be there. So this stress function will be there for both circular and non-circular sections. Both circular and non-circular. Now the question is how to find the angle of twist, how to find the shear stress in the case of non-circular sections. Before that, anyway, in this class, for non-circular section I have done the derivation for electrical, and of course these I have done problems. We can just go through that. Today I will explain how we can show that this psi is equal to 0 for circular sections, as well as how to evaluate the stresses, shear stresses in circular sections. So now I will take the heading as circular sections, torsion of circular sections. That also he has asked in question paper, in some other question papers he has asked that also, derivation. So torsion of circular cross section. To derive the expressions for the torsion of circular cross section. So you know that for a circular cross section, what is the equation of the boundary of a circle? Anybody? What is the x-axis? This is x-axis. I will take x-axis from the centroid this side. This is x-axis. The y-axis. Let me take the radius as r. R is the radius of circular section. Now the question is, what is the equation of this boundary? This is the boundary. Now this circular section is subjected to torque. So what is the equation of circle? What is the equation of circle? So T is the torque, right? I will take the torque like this. T is the torque. This is the origin. Torque is also same as twisting moment. Yellow on there. Torque on there, twisting moment. That's what torsion. The torque is another word. So which is normally in Newton or kilonewton. Now what is the equation of this boundary? So we have to start from that equation of a circle with radius r and center at the origin. What is the equation of the circle? Equation of circular boundary. In geometry I have learned analytical geometry. X square plus y square is equal to r square. What? The equation where xy is a point. Anyway you can take the point. P is the point xy. So x square plus y square is equal to r square is the equation of the circular boundary with origin as center and radius r. Now from this we can assume stress function. Let stress function B phi is equal to phi is the stress function rho into x square plus y square minus r square. This is the stress function we will assume. So we have to assume the stress function for a circular boundary like this because it resembles this equation. You will bring this r square this side, it becomes x square plus y square minus r square and multiplied by some constant. So rho is a constant. So instead of taking k, I have taken it as rho. So that is the stress function. Now this has to satisfy one equation called Poisson's equation, which I have derived. I will write the Poisson's equation here directly. So this phi should satisfy one equation called Poisson's equation. Poisson's equation. So this Poisson's equation is given by del square phi is equal to minus 2g theta. That is the Poisson's equation. I have derived this. You can refer in one of the videos I have derived this. So you can directly del square phi is equal to minus 2g theta is the Poisson's ratio for torsion. Now here phi is the stress function, g is the Young's modulus of rigidity or shear modulus, theta is the angle of twist. So this equation should be satisfied now. Let us find out that del square phi is nothing but dou square phi by dou x square plus dou square phi by dou y square. Please note that this I have explained earlier also. Harmonic equation, correct? Harmonic operator. So del square phi is nothing but dou square phi by dou x square plus dou square phi by dou x. This is del square. Now let us find out this. So we have phi as rho into x square plus y square minus r square. Differentiate this with respect to x. Dou phi by dou x. Treat y as constant, rho as constant. R is also constant here. What happens? Rho into 2x, correct? Because y is constant and r is constant, we have only one term. Once again we differentiate with respect to s. Dou square phi by dou x square is equal to 2 times rho. Similarly, you differentiate with respect to y. Dou phi by dou y is rho into 2y. Instead of x, y will come. Once again, you differentiate. Dou square phi by dou y square is equal to 2 times rho. Got it? Sarina? You can substitute in that equation, this equation. Poisson's equation, we call it as 1. So substituting in 1. So 1 is del square phi is equal to minus 2 theta. Substitute. So this is dou square phi by dou x square plus dou square phi by dou y square is equal to minus 2 theta. That means this is, we substitute this is 2 rho plus 2 rho is equal to minus 2 theta. Correct? So 2 can be 2 rho plus 2 rho is 4 rho. So from this rho will be what? So this is 4 rho is equal to minus 2 theta. Therefore rho is equal to minus 3 theta by theta. Rho is minus g theta by 2. This is what you get. Now substitute this rho in this. So we have the stress function phi is equal to rho into x square plus y square minus r square. So substituting for rho is this. So phi is equal to minus g theta by 2 into x square plus y square minus. This is what you get. You call this as 2 equation. Common. Now we have one more equation which I have explained in the earlier video. We have this relation between this torque T and this stress function phi. So torque T is given by, please note, 2 times double integral phi dx dy. This I have explained in the earlier video. So refer. So just remember this. So T is equal to 2 times double integral. Why it is double integral? Because there are 2 variables, dx and dy. They are the 2 variables. Now using this, now we can substitute for phi now there. So substitute for phi. Substituting for phi. So phi is this. Minus d theta by 2 into x square plus y square minus x r square. We just substitute that there. So t is equal to 2 into double integral minus g theta by 2 into x square plus y square minus r square into dx. Correct? Like that we get. So this 2 and 2 will get cancelled. So minus d theta, you can take it outside, and you can differentiate this separately. So please note that the dx into dy is nothing but dA. So why it is dA means, suppose if you take an elemental strip like this is dx, and another strip like this is dy in y direction. This area is taken, this is your, got it? Achal the work. In x direction, I have taken elemental strip. In y direction, I have taken elemental strip. So this is dx, this is dy. If you take this area, this is dx into dy, that is dA, elemental area. That means this can be written like this now. T is equal to minus d theta is constant. You can take it outside. Only x and y they are the variables. So what I can write here is double integral x square dA. I will separate the terms now. Double integral x square dA. This is dA plus double integral y square dA minus double integral r square. I have separated the terms. This double integral becomes a simple integral when you differentiate with respect to A over the area A. So double integral will be there when you take dx dy. When it is converted to dA, single term, then it becomes single integral. Please note that double integral dx dy is the same as single integral d. That's how much. So dx dy double integral will be the same as this. Okay? That's what I have made. Now, if you integrate these things, what you are going to get, let us see. So now we have to use the concept of moment of inertia. Moment of inertia concept is the concept. According to this moment of inertia concept, Ixx is the moment of inertia of any area about x-axis. This is given by integral y square dA, whereas Iyy is the moment of inertia of any area about y-axis is given by integral x square dA. Integral x square dA. Yes. Now we have to substitute these things there. So in the case of a circular cross section, this Ixx and Iyy they are equal because it is symmetrical about both x and y axis. And if you derive the formula for moment of inertia, you are going to get pi e power 4 by 64 as the moment of inertia. So these things we have learned in your mechanics or SOM earlier. Directly you can write that d, you can get it as 2r, so that means it is pi into 2r to the power 4 by 64, or this can be written as pi r power 4 by 4. So this is also pi r power 4 by 4. Please note that both are equal to pi r power 4 by 4. So the first and second terms are equated to pi r power 4 by 4. Yes. Now, if you substitute this here, T is equal to minus d theta into what is this? Integral x square dA is pi r power 4 by 4 plus this is also same pi r power 4 by 4 minus this integral r square dA. We can prove that it is pi r power 4. You can just directly write this. So you write here integral r square dA is pi r power 4. You can directly write it. You can show this, but anyway, you can directly write it. So this value you can directly write. Now if you simplify this, T is equal to minus d theta into this becomes pi r power 4 by 2. This plus this. Minus pi r power 4, that is minus d theta into minus pi r power 4 by 2. If you do this subtraction, you get this minus into minus will get cancelled, will be plus. So finally it will be, what is that? You are going to get d theta into pi r power 4 by 2. Correct? This pi r power 4 by 2 is nothing but the polar moment of inertia of circular section. So finally you got T is equal to g theta into g. So this is what you got. Actually, in that torsion equation, T by J is equal to G theta by L, I have taken. Is it correct? In that pure torsion equation. In that, if you take L as 1 meter, you are going to get this. T by J is equal to G theta. Same thing you are going to get. That means it is torsion per unit length. That is the meaning of that. Now, this is the expression for torsion in the case of circular section. So, torsion expression we got. Next, after this, we need to find the shear stress expression also. So, we got torsion expression for the circular section. Torsion in circular cross section. Then shear stresses. So these equations already I have explained in the earlier video. You can go through. So there will be two shear stresses in the case of torsion. One is tau xz and another is tau yz. So these two are the torsion. Please note that tau xz and tau yz, they are the shear stresses. This tau xy will be 0. This is very important. In torsion, one of the shear stresses will be 0. This tau xz is given by dou phi by dou y. This is given by dou phi by dou y, whereas tau yz is given by minus dou phi by dou x. So better remember these two expressions. So dou phi by dou y is tau xz, and dou minus dou phi by dou x is tau yz. So only two shear stress components will be there. The third one will be 0. Now if you differentiate this, so you got phi as, this is phi, so this is phi, or this is phi. You can take this as phi. You differentiate this with respect to y now. You differentiate this with respect to y. So what you are going to get? So that is minus d theta by 2. You can write like this. Minus d theta by 2 is constant. And what is the derivative now? We are differentiating with respect to y now. So it becomes 2y. Correct? Other two are constant. That means you are getting minus d theta y. Correct? Minus d theta y. Whereas here, if you take minus dou phi by dou x, means this is already minus is there, minus into minus becomes plus, d theta by this constant into x you are going to get, which is plus d theta. So these are the expressions for shear stresses, and the resultant shear stress is given by tau, that is given by tau square xz plus tau square yz under root. So therefore tau is equal to, I can take this as minus g theta y square plus g theta x square, like this. This is resultant shear stress. So one shear stress will be like this, another shear stress will be like this. The resultant of these two is tau, like this. This is tau. So this tau is given by this formula. So tau is, now if you simplify this, g square theta square y square plus g square theta square x square under root. So g and theta you can take common here. So g square theta square into y square plus x square under root. Square root of this will be g and theta, and here this is root of y square plus x square. You know that x square plus y square is equal to r square. Therefore, this is root of d theta into root r square, which is nothing but d theta into r. So what you can say here is therefore tau is equal to g theta into r. See how we get the relation. This is the shear stress. Resultant shear stress. So one expression we got for torsion, second expression we got for resultant shear stress. So g theta into j is for torsion or the twist, whereas g theta into r is for the shear stress. So this is for the twist, this is for shear stress. So expression for shear stress as well as expression for torsion. Suppose if you take theta as the angle of twist per unit length. If theta is the angle of shift, angle of twist per unit length, theta, if theta is equal to angle of twist per unit length, then we have the first equation E is equal to g theta j. Therefore, T by j is equal to g theta. First equation. Second equation, we got tau is equal to g theta into r. Therefore, tau by r is equal to g theta. So if you combine these two equations, you get the equation T by j is equal to g theta is equal to tau by r. This is your equation. Please note that in pure torsion equation, if you put L is equal to 1, you are going to get this. That's all. Pure torsion equation, d theta by L will come there. I have written initially. If you put L is equal to 1, that means per unit length. That is the meaning. Per unit length means the meaning of that is you are taking per unit length of the shaft. 1 meter, 1 mm, whatever it is. L is equal to 1. That is it. Now the last step we have to prove that it does not have any warping. Circular section does not have any warping. So that ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? ಸುಮ್ಮನೆ ಬರ್ಕೊಳ್ತಾ ಇದ್ದೀರಾ? ಅರ್ಥ ಮಾಡ್ಕೊಂಡು ಬರ್ಕೊಬೇಕು. ಬರ್ತವೆ ಎರಡು ಸಾವಿರ ಪ್ರಾಕ್ಟೀಸ್ ಮಾಡೋದು ಇದೆಲ್ಲ ಈಸಿ ಇದೆ. ಓನ್ಲಿ ಥಿಂಗ್ ಇಸ್ ಹ್ಯಾವ್ ಅಸ್ಯೂಮ್ ದಿ ಶಿಯರ್ ಸ್ಟ್ರೆಸ್ ಫಂಕ್ಷನ್ ಇನ್ ದಿ ಬಿಗಿನಿಂಗ್ x square plus y square minus r square ಅಂತ. Then use this concept t is equal to 2 double integral phi dx dy. This dx dy is replaced by dA, and double integral will be converted to single integral. Evaluate the integral, you will get the expression for t, twist, the torsion moment. And then use these two formulas to find the shear stresses. In the case of torsion, tau xy will be 0. That is very important. Tau xy will not be there. Only tau xz and tau yz will be there. Now using that we can prove the pure torsion equation. Now we have to show that there is no warping. So to prove psi is equal to 0. No warping in circular section. In non-circular sections, warping will be 0. Now let us see how we can prove psi is equal to 0. For that, we have to use another relation between the shear stress and the warping function psi. All those equations are explained in those earlier video lectures. So we have to recall that expression. So the expression which gives the relationship between the warping function and this shear stress is one expression I use. Tau xz is equal. So we have. So we can directly use this. Tau xz is equal to g theta into dou psi by dou x minus y. Yeah, this is the expression we have to use to prove psi is equal to 0. So we have one more relation in terms of phi. So what is that? So this is the first relation. We have what? Second, we also know that tau xz is equal to what? Here I have done dou phi by dou y. Tau xz is dou phi by dou. So these two we have to equate to. Both are equal to tau xz only. So we have to equate these two. These two we have to equate. So what is dou phi by dou y? We got it as minus d theta y. So this is nothing but, so dou phi by dou y, we have already proved that it is minus d theta y. That means this should be equal to minus d theta y. Therefore, equating 1 and 2, equating RHS of 1 and 2. LHS is same, therefore RHS should be equal. So g theta into dou psi by dou x minus y should be equal to minus d theta. Okay. Now you simplify this. So g theta into dou psi by dou x minus d theta y is equal to minus d theta. So this term will get cancelled because both minus d theta y. So this should be 0. D theta into dou psi by dou x is equal to 0, or this cannot be 0, therefore dou psi by dou x should be 0, therefore this is equal. Therefore no warping in circular sections. Psi is equal to 0. This is the only section with no warping. Only in circular sections we won't find out of plane displacements due to torsion, whereas in non-circular sections, whatever it is, whether it is tubular section or rectangular or elliptical, triangular, T section, I section, whatever it is subjected to warping. So this is how we can prove psi is equal to 0. There are two important functions. Psi is called as the warping function, which is 0 in the case of circular section. We can prove like this. And phi is the stress function. Stress function depends on the type of the cross section. For circular sections, it is x square plus y square minus r square. Rho into x square plus y square minus r square. Whereas for elliptical section, it is different. So you have to take the equation of ellipse, and based on that, you have to decide the phi function, stress function for elliptical section. So I have done both the derivations. So earlier I have done the elliptical in one of the videos. You go through that. In this I have done for circular. So one of them may be given in the examination, and also I have done the derivation of this also. Dou square phi is equal to minus 2g. This also I have derived. Derivation I have done in one of the videos. You just go through that. So totally 3 derivations are there. One for circular, one for elliptical, and this is general. This is the Poisson's equation. General Poisson's equation. How to get this equation? This also I have done in one of the equations. So 3 derivations will be there. one of them they may give, and one problem they may give. 10 marks for derivation, 10 marks for problem. So problems I have done in those videos. Of course, I will be doing one or two problems. I will explain how to do for non-circular sections. Usually tubular sections, those things how to do, I will explain.